Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
Earlier this year, Brian Butterworth decided to figure out how many numbers the average person encounters in a day. He picked a Saturday for his self-experiment. As a cognitive neuroscientist and professor emeritus at University College London, Butterworth works with numbers, so a typical weekday wouldn't have been fair. He went about his day as usual, but kept track of how frequently he saw or heard a number, whether that was a symbol, such as 4 or 5, or a word such as 4 or 5. He flicked through the newspaper, listened to the radio, popped out for a bit of shopping, taking special note of price tags and "Would you like to take a guess?" he asks me when we speak over Zoom a couple of weeks later. I hazard that it's well into the hundreds, but admit I've never thought about it before. He says, "I reckon that I experienced about 1,000 numbers an hour. 1,000 numbers an hour is 16,000 numbers a day, is about 5 or 6 million a year. That's an awful lot of numbers. I reckon that I experienced about 1,000 numbers an hour." Brian Butterworth University College London Butterworth didn't conduct his thought experiment just to satisfy his own curiosity. He's including the calculation in an upcoming book, Can Fish Count?, slated for publication next year. In it, he argues that humans and other animals are constantly exposed to and make use of numbers, not just in the form of symbols and words, but as quantities of objects, of events, and of abstract concepts. Indeed, that most humans, even from a very early age, can quickly and accurately distinguish among different quantities of things is so obvious that it's frequently taken for granted. This ability, known as numerosity perception, is distinct from counting, the process of keeping a tally while going through a set of objects, and is present in infants long before they learn words or symbols for particular numbers. It is evident, too, among adults in isolated human populations that typically don't use numbers much in their daily lives. While some scientists propose that the so-called sense of number is just an offshoot of a more general perception of magnitude, an ability to say roughly how big something is in relation to something else, others argue that numerosity perception is an independent phenomenon, something that gives a SPE. Some scientists assign this number sense an even greater importance, claiming that it's the foundation for humans' capacity for numerical reasoning and arithmetic, that there's a connection between our ability to quickly recognize the number of flowers in a vase, and our ability to understand why 2+. Thanks to growing interest in the subject, combined with advances in experimental and technological methods for studying the brain, data are trickling in to support these arguments, and occasionally confuse them. The result is far from being a clear picture, and disagreements still abound, but for Butterworth and others like him, multiple threads of evidence are now coming together to support numerosity, and our brain's encoding of it, as a fundamental part of how we experience the world. Making the case for human sense of number when David Burr first shared what would become some of his most famous work on numerosity perception around a decade ago, he was taken aback by the heckling he received. His findings, he'd argued to the crowd at a visual perception conference, indicated that humans automatically perceived an image's numerosity in much the same way they perceive its color. But, some very angry people were yelling from the audience, "It's got nothing to do with number," he recalls. A classic example is the color illusion in which staring at a red square for 30 seconds will cause you to perceive a white square as bluish-green. Psychologists interpret the existence of such adaptation effects as evidence of dedicated neural mechanisms for seeing color, and, accordingly, of color's importance to how we perceive the world. Control experiments with dots and different patterns and densities indicated that the effect was specific to the number of dots, Burr adds, and not, as the hecklers were yelling, to some other quality of the image, such as the density of the dot pattern. This finding put number in the same category as color, motion, texture, and other visual attributes as something that the brain automatically picks up on, the pair wrote in a 2008 paper describing the results. We propose that just as we have a direct visual sense of the reddishness of half a dozen ripe cherries, so we do of their sixishness. The argument about whether numerosity is a fundamental feature of perception hardwired into our brains, or just a byproduct of perceiving something else, has Kant. For images with more than 50, perhaps 100 objects, Burr says, it's likely that object density, or what's known as texture, does take over as the feature our brains are using to estimate quantity. Closing parenthesis. Some researchers have explored the idea using imaging techniques to study patterns of activity in the brain as people perform numerosity tasks. They've found in multiple studies that activity in the visual cortex is particularly sensitive to numerosity. Changing the number of dots causes bigger spikes in activity than changes in other visual metrics, even when people aren't asked to pay attention to how many dots they're seeing. While some scientists propose that the so-called sense of number is just an offshoot of a more general perception of magnitude, others argue that numerosity perception is an independent phenomenon. Burr has found that adaptation effects can be elicited with sequences of flashes. People who see a fast series of flashes will underestimate the number of flashes in a medium-paced sequence, for example. And Utrecht University's Ben Harvey and colleagues have recently studied brain activity in people exploring different numbers of objects placed in their hands, a task designed to test so-called haptic numerosity. Using fMRI, they compared brain activity during this task with that of a visual nummy. It seems that at least somewhere in the processing of numerosity, too, the brain recognizes a connection between all these different formats, that 3 dots and 3 beeps are both versions of 3. Burr has tried mixing types of stimuli in his adaptation experiments, and found that, a spatial display of 20 dots would appear like 15, let's say, if you had been adapted to a fast sequence of either sounds or flashes, he says. It really gives us this idea of a generalized sense of number. Neural mechanisms representing number in the brain. One clue about what a general number sensing mechanism might look like, neurologically speaking, comes from the kinds of mistakes humans make when estimating or discriminating between. People will often confuse similar quantities. For example, they might have difficulty quickly telling the difference between a plate of 8 chocolates and a plate of 9 chocolates. Burr and many other researchers have repeatedly shown that this kind of error tends to get worse the smaller the proportional difference between two numbers. You're more likely to confuse 23 chocolates with 25 than to confuse 3 with 5 or 10 with 40. People tend to get better at perceiving numbers of objects as they age. Children are better at distinguishing similar numerosities than young infants are, and adults are more precise still. Partly based on these observations, scientists have come up with a proposed cognitive system thought to be involved in numerosity estimation, the approximate number system, ANS. This system could receive sensory information from the visual cortex, say, and extract the quantity of things in a way that gets less precise with magnitude. By the time he started working on the problem around the turn of the millennium, fMRI studies by cognitive neuroscientist Stanislas Dehaene and others had started to link numerical processing in humans to particular brain regions such as the interparietal sulcus, IPS, a groove in the parietal lobe. In some of their earliest experiments, Nieder and colleagues recorded from hundreds of individual neurons in the brains of macaques trained to discriminate between small numbers of dots on a screen. In a handful of studies in the 2000s and 2010s, the team reported that certain neurons in the macaque IPS and prefrontal cortex, an area typically associated with higher cognitive processes such as planning and decision-making, were specifically sensitive to certain numerosities. That is, a particular neuron has highest activity to a specific preferred or beloved number, say 3, Nieder says. The same group also reported that the breadth of a particular neuron's range, how likely it was to fire at quantities near but not equal to its preferred number, increased with increasing magnitude. A 12 preferring neuron was far more responsive to pictures of 11 and 13 items, say, than a 3 prefer. The researchers later recorded from the brains of crows trained to discriminate 1 to 5 items. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.